So this week we're looking at populations rather than individuals. So far, every time we've been looking at genetics, we've been looking at a single individual or an individual and their parents, or maybe, with the pedigrees, a larger family tree. But even with the pedigrees, we're still focused on single individuals at a time. With population genetics, we're looking at whole populations at once. So when we do this, we can't look at individual numbers. Instead, we need to be looking at frequencies or percentages so that we can compare one population to another. So if we look at our population, and let's say we have a population of 100 people. So 100 people. And of these 100 people, we're going to just use the letter H here. Okay? So let's say that 30 people are big H, and let's say that 25 people are big H, little h, and for homozygous recessive, we have 45 people. So if we total that up, we've got 100 people in our population. Now, these numbers are super helpful to us, but if I wanted to compare this population to another population that has, let's say, 150 people, it's not going to give us a very good comparison. So instead, what we want to do is we want to change these into frequencies, okay, or percentages, if that makes more sense to you. So how we do this is we take the number of people with the particular genotype and divide by our total number of people. We have 30 divided by 100, 25 divided by 100, 45 divided by 100 to get our frequencies. Okay, so that's going to mean 30 divided by 100 is going to be 0.3. 25 divided by 100, 0.25. And 35 divided by 100 is going to be 0.45. Now, if I total those up, I should equal 1.0, because that's one whole population. This is what we call the observed genotype frequency. Okay, it's observed because it's what we have in our living population. And it's a frequency because it's a percentage. It's in relationship to the other alleles. Now, this will become really, really important at the end of our equation. Okay, but for the moment, this is basically what we're looking for, is we're looking for these genotype frequencies. Now, in order to kind of go any farther, we need some common terminology. So, when we're dealing with frequencies of alleles, called allele frequencies, we can't use the letters h and little h because those represent actual alleles, numbers of alleles. So instead, to find out or to compare and get those frequencies, we use the letters P and the letter Q. So P represents the frequency of the dominant allele, and Q the frequency of the recessive allele. All right. So in order to find these numbers, we need those original numbers that we started with. So we have H, big H, big H, little h, and little h, little h. We had 30, 25, and 40. Those are our actual numbers. That's 100 people. So to find our frequencies, okay, to figure out, first we need the total number of each allele. So we're just going to have a little bracket of big H and little h's. Now these 30 people each have 2 big H's. So we're going to take that 30, we're going to multiply by 2 to give us 60 big H's for them, and no little h's. Now these 25 people here, they have one of each, right? So if they have one of each, then we're not going to multiply by 2. Instead, we know they've got 25 big H's and 5 little h's. Okay, so make sure you don't multiply this one by 2. But if we add these together at the end here, then we do equal double our number. Lastly, look at our homozygous recessive. We have 45 individuals. So we have no big H's because they each have 2. We can multiply by 2, which is going to give us 90. Okay, little h allele from those individuals. Now we're going to total these up. So 65 plus 25 equals 85. 25 plus 95 equals 115. That's our total number of alleles in our population. But again, we want frequencies. So to find our frequency, we have to divide by the total number of alleles. So we add these two together to get our total. So 85 plus 115 is going to equal 200. Right? And it should equal double our number of people. Right? Now then, we're just going to divide these by our total. So 85 divided by 200 and 115 divided by 200. And since I'm running out of space, I'm going to move over a bit. So my 85 divided by 200, 85 divided by 200, that's going to give me 0.425, and that's going to be P, and the dominant allele. Q, I'm going to take 115, I'm going to divide that by 200, and that's going to equal 0.5575, and again, that's Q. Okay, that's the frequency of the recessive allele. So far, we've determined our observed genotype frequency, and now we just discovered our observed allele frequency. Okay, observed allele frequency. So again, this is what we do have in our living population. Now, what we want, though, is we want to know, is this living population changing? Is it going to be different in our next generation? Are our frequencies going to be different? Now, in order to figure that out, we have to do a mathematical process called the Hardyweinberg equation. And what that's going to do for us is it's going to help us determine what the population should be in our next generation, what we would expect to be based on our observed allele frequencies. That's going to be our key. So if we keep moving on here, with a population, when we're looking at what we should have, we have to take our population of females and our population of males, and we have to cross them because we're looking at reproduction here. We have to take into account all possible alleles. Now, if we go back to our Q's back here, if Q is the frequency of the dominant allele and Q is the frequency of the recessive allele, then P plus Q has to equal 1, 0 for any given population. If we go back to our males and females here, our female population within our overall population is going to be P plus Q, and our male population is going to be the same, P plus Q. Right? Now both of those equal 1. It's 1 and 1. Now what we want to do is we want to multiply these populations because we want to account for all possible interbreeding between them. Okay? Now 1 times 1, hopefully you remember, is 1. This, however, is a little bit harder to deal with, so we need to make it make more sense to us. So we can use that fun little mathematical process called FOIL. You might remember it from algebra. So we would take P times P, and that's going to be P squared. Then we're going to go P times Q. Okay, and since we've got a plus symbol here, we're going to go plus PQ. And then we're going to go Q times P, and we want to keep it in the same order, so we're going to go plus PQ again. And then we're going to go Q times Q, which is going to give us Q squared. Now, if P plus Q equaled 1 and P plus Q equaled 1, 1 times 1 is 1, so this whole equation should equal out to 1. Now, still not the easiest equation to work with, so we want to do one more thing here. We want to combine like terms, these two here, which is going to give us an equation of p squared plus 2pq plus q squared equals 1. Now, these terms, p squared, 2pq, and q squared, each represent a specific genotype. So if we think about the fact that p indicates the dominant allele, p squared then is going to be the frequency of the homozygous dominant genotype. 2pq, since we have 1p and 1q, that's going to be the frequency of our heterozygous. What I said. Okay, frequency of our hetero. And then q squared, that's going to be the frequency of our recessive. So that's going to be our frequency, our homozygous recessive genotype. Now these genotypes, all three of these are what we call our expected genotype frequencies. Expected. This is what we should have in our population if our population is not changing generation, generation, generation. So what we should have if we are not changing. Okay, so hopefully you're with me so far. We've got our observed genotype frequencies, and that's these guys. That's what we do have in our living population. We have our observed allele frequencies, again, still what we have in our living population, but this time we're looking at the alleles themselves rather than the genotypes. And then with our equation, okay, we end up with our expected genotype frequencies, what we should have if the population is not changing. Next, I'm going to show you how to use this equation. So now that we know how to come up with our observed allele frequencies and our observed genotype frequencies, now to use that equation, all we have to do is plug those numbers into the equation. So what we had here was P equaling 0.425 and Q equaling 0.57. Now, plug this into our equation. We're going to take 0.425 squared, that's P squared, plus 2 times 0.425 times 0.575. That's for 2PQ, plus 0.575 squared. There's our Q squared. And again, we know this equals 1. So there's our equation. Now, in order to figure any of this out, we don't want to just plug it into the calculator because that's going to give us just 1. That's not going to give us any important information. Instead, we need to take each part individually because we really want this number, and this number. So if I take 0.425 and I go 0.425 times 0.425, I get 0.18. And it's a much longer number than that, but I'm going to round to 2 digits. Then I'm going to go 2 times 0.425 times 0.575, and I'm going to get 0.49. Now in reality, I got 0.48875, But again, we want to go ahead and round to 2 digits just to make our life nice and easy. Then I'm going to go 0.575 times 0.575, and that's going to equal 0.33. Again, it's a much longer number. I'm just going to round. Now, if you have a square button on your calculator, you can use that, or you can just multiply them. Remember that p squared is really p times p, and q squared is q times q. But just for a double check, I'm going to add these together to make 100% sure they equal 1, which in this case they do, 1.0. Now, occasionally, because you're rounding, you may end up with 1.01, or you may end up with 0.99. That's okay. Now, the big thing to remember here is that what you have just determined are your expected genotype frequencies. Okay, your expected frequency. And this one here, that's for homozygous dominant. This is for hetero. And this one's for homozygous recessive. So those are the numbers, those are the percentages, the frequencies that we should have if the population is not changing, not evolving. So what we want to do then is take these expected frequencies and compare them back to the observed frequencies, the ones that we actually do have. So if you remember back, this was our observed frequencies. So let's just put this all together on one page. Just to make it, not too far. There we go. Just to make it easier for us to do if we have it all in one spot. So our big H, okay, big H, little h, and then little h. Our observed, I'm just going to put OB, 1.3, 0.25, and 0.45. Our expected, what we just calculated, so for the homozygous dominant, in this column here, we're going to have 0.18, and then in this column, right, we're going to have 0.49, and down here we're going to have 0.3. Now, what you're seeing here is that these numbers would equal if the population was not evolving. Now, these numbers obviously do not equal, not a single one of them is the same. Therefore, the population is not in equilibrium, so we say that the population is evolving. So if our observed equals our expected frequencies, then equilibrium. Population is not changing. If our observed does not equal our expected, they're not the same, then we have evolution. And we have evolution. The population is changing. So here, not changing. And then here, evolution, our population is changing. Okay, so that's the difference. The expected equals the observed, population is in equilibrium. Expected does not equal the observed, the population is evolving. So now at this point, you should be able to complete several of the exercises in chapter, what chapter are we in right now? Chapter 8? Chapter 8, chapter 9? Chapter 8. So you'll be able to complete the first half of chapter 8, determining the observed frequencies, determining the observed allele frequencies, determining expected frequencies, and working through the whole process to determine, is the population in equilibrium or is the population evolving? Is it in evolution? Okay, that's where you're going to stop at home. In class, we will be looking at the forces of evolution. What's pushing this change? Why is it that we never in nature actually see population that's truly in equilibrium. Okay, that will be, you'll have a video on why, and the exercises for that second half of the chapter you will be completing in class next week.